Okay, the next question is the pendulum. A bit hard doing this without doing simple harmonic motion, especially this first question, but let's get into it anyway. So here they're saying that the pendulum has been pulled out to the side, and they want us to describe how the forces acting on the bob change the bob's speed as it travels. Cool, so we just basically need to consider if the forces are balanced or unbalanced, and if they're unbalanced, in what direction is the pendulum accelerating, and how does that affect the velocity of the bob. So there's two forces acting here. There's the weight force, which always acts vertically downwards, and because the mass of the pendulum isn't changing, this weight force is constant regardless of where it is in the oscillation. Then the other force is the tension force, and the tension force is always going to act in the direction of the string. So it's these two forces that cause the motion of the bob to change over time, which means the speed of the bob to change over time. So in this scenario here, which is when it's displaced out to the left, the tension force is back in an angle like this, and you'll notice that it has a horizontal component and the weight force does not, which means these forces cannot be balanced, which means the bob is going to accelerate towards the equilibrium. Now if angle's less than 7 degrees, we can say that the unbalanced force approximates the horizontal. If the angle's greater than 7 degrees, then the unbalanced force will sort of be downwards in an angle like this. As the bob comes back towards the equilibrium, which is like the rest position in the middle, the tension force will point up, which means the size of the unbalanced force, the resultant force, will decrease over time as the horizontal component of the tension force decreases. In the answers, it says that at the equilibrium position, when it's moving through the equilibrium position, the forces are balanced. Now I'm going to have to disagree with that, because the bob is moving when it passes through the central position. Its speed is not changing, but its velocity is, so it's still accelerating, but it's just accelerating upwards when it passes through the middle or the equilibrium position. So basically, to answer the question, the speed of the bob increases towards the equilibrium position because there is these two forces add to give an unbalanced force. Alright, moving on to question C. The bob is released in such a way that the swing is now horizontal, so it's going around like this, which is called a conical pendulum. And we need to do two things. We need to first work out the angle in here, and then when we've got the angle, show that the tension force is 18 newtons. Cool. So the way we do that is first look at a displacement vector diagram. So we've got this angle up here. The length of this side here, which is the length of the string, is 1.55 meters, and the length of the radius, which is this part here of the triangle, is 0.290 meters. And we just need to calculate this angle up here. So the way we do that is sine theta. This is question CI, by the way. Sine theta is equal to this here, 0.290, divided by the hypotenuse. And then we're solving for theta, so we need to do inverse sine of these two numbers here. Oopsie. And we solve and we get an angle of 10.78 degrees. Right, so then the next part is we need to do a force diagram to consider the forces here. So let's go with the weight force is acting vertically downwards, like so, and the tension force is acting upwards. I might just redraw this a different way, sorry, just to make it sort of match conceptually. So it doesn't matter what way you add vectors together, you're going to get the same answer. You can add them in either order. I'm actually going to start by drawing the tension force. So the tension force acts upwards like this, which is in the direction of the string, and then the weight force acts vertically downwards, like so. In the conical pendulum, the vertical forces are balanced, so the mass doesn't accelerate upwards or downwards, which means the centripetal force must be horizontal. And it is the resultant, or the total force of these two forces. And the total is drawn from the first tail to the last head. So this is the centripetal force here. And the reason I redrew this is just to make it a bit more identical to this triangle up here. This is the angle theta, which is the same angle as we calculated above. Cool, so now we can just use some trigonometry again to work this out. This time we need to use, because we know this is equal to mg, we can use cosine theta here. So cosine theta equals the weight force over the hypotenuse, which is the tension force. And we can rearrange this to make tension the subject, which is the weight force, or mg, over cosine theta. And we just substitute in here the mass, gravitational field strength, and divide it by cosine of the angle that we calculated in the previous question, or the previous part of this question, and we come out with a force of 17.975 newtons, which is equal to 18 newtons to 2 significant figures, which is what the answer or the question says it should be. Well done me. I've done it again, laid out my work in a strange way. So now on to question CII. For this one, we need to calculate the speed that the mass must have been given when released in order to obtain a horizontal circular path at a radius of 0.290 meters. So I'll go over here now for this one. So I'm thinking about an equation with velocity in it. That's to do with circular motion, so it's probably to do with this one. Over R. So we've calculated the tension force here. We haven't calculated the centripetal force, so I should be able to work that out as well. So let's, I'm going to rearrange this equation first to make velocity the subject. So I'm going to bring the R to the other side. So it's on the bottom on this side, so it goes to the top now over this side here. And I'm going to take the mass from the top on this side, so it goes to the bottom on this side of the equals. And that's going to be equal to the velocity squared. So I'm going to take the square to the other side as well, and we get square root. Okay, so I know that and I know that, but I don't know that. So I'm going to need to get that. And I can go back over here to my force diagram and use that to work out the size of the centripetal force. And I'm going to use Pythagoras, just for a change, because I've done lots of trig. You can do this using trigonometry as well. I know that the centripetal force here is going to be equal to the square root of the hypotenuse squared minus this other side of the right angle triangle squared. And each of these are known forces. So I can substitute those in. I've got my tension force, which is 17.975 squared, minus the weight force, which is 17.658 squared, and I get a centripetal force of 3.3631 newtons. I can then use that force over here in this equation to solve for velocity. So velocity equals the square root of 3.3631 times the radius 0.290 divided by the mass, which I wrote somewhere, there we go, 1.80, and then solve and you get a velocity of 0.74 meters per second to 2 significant figures. Okay, we've got one more question to go.